What does it take to mass produce KitKat, Corny bars, and Mars at full speed without the layers cracking? If there's even one tiny mistake in the production line, the entire product falls apart. Today, we follow the lines from mixing and baking to layering, revealing the rigorous precision that is required to produce these chocolate giants. KitKat is assembled from a dry, crisp wafer core that is first strengthened and sealed by contact with a warm, fat-based filling, then coated in chocolate, then cooled so the wafer stays crunchy and the bar snaps cleanly on the finger lines. The wafer stream begins as a thin batter system that must bake into sheets with low moisture and uniform thickness. Flour is sieved to remove lumps and to stabilize hydration. Sugar and salt are weighed precisely because they affect browning and sheet brittleness. Water is tempered so batter viscosity stays consistent at the depositor. A small fat or emulsifier addition is used to control plate release and sheet texture. The batter is mixed only until smooth because excessive mixing increases gluten development and makes sheets tough and less crisp. Batter viscosity is one of the main controls because it determines how evenly the batter spreads on wafer plates. The batter is held in a feed tank with gentle agitation to prevent settling of flour fines. From there, it is pumped to wafer irons. Each iron is a pair of heated plates that close, bake, and open in a cycle. A metered dose of batter is deposited onto the plate and spreads under closing pressure. Heat drives rapid water evaporation and sets the starch matrix into a porous, brittle sheet. Bake time is tuned so the sheet dries to low moisture without scorching, because scorch creates bitter notes and weak zones. When the plates open, the wafer sheet is released and moved to cooling. Cooling stabilizes crispness and prevents warping. The sheet is then cut into finger-sized leaves. Cutting uses sharp rotary blades to avoid cracking edges. At this stage, the wafer leaves are extremely brittle and must be handled with low-impact conveyors and minimal drop heights to prevent breakage before lamination. Lamination creates the multi-layer wafer block that defines the bar bite. A thin layer of wafer creme is applied between leaves as an adhesive and moisture barrier. This creme is not the outer chocolate, but a fat-based filling designed to soak slightly into wafer pores and then set. The creme is prepared by blending sugar, cocoa components, milk powders, and fat into a smooth paste with controlled viscosity. Particle size is refined so it spreads evenly and does not feel gritty. The creme is held warm enough to flow, but not so warm that it becomes runny and floods the wafer. Assembly stacks alternating wafer leaves and cream layers. A depositor spreads cream onto a wafer leaf in a uniform film. Another leaf is placed on top, and the stack repeats until the target number of layers is reached. Alignment matters because misaligned leaves create uneven edges and weak points at the snap lines. Light compression follows stacking to ensure contact and eliminate air gaps. Compression must be controlled because excessive force crushes wafer cells and reduces crispness. After stacking, the wafer block enters a setting tunnel. This tunnel cools the block so the creme fat network crystallizes and locks the layers together. The block must become rigid enough for cutting, but not so cold that wafer becomes overly brittle and shatters. The setting profile is staged so the outer surfaces firm first and then the core equalizes. Once set, the block is cut into sticks and then into the familiar finger format. A longitudinal cutter slices the block into wide slabs. A second cutter defines the number of fingers per bar by cutting grooves or separating lanes. A cross cutter then creates bar lengths. Knife sharpness and speed are tuned to avoid crushing the wafer. Ultrasonic knives can be used in some lines to reduce drag through the cream layers and keep edges sharp. The cut wafer fingers are then routed into an enrobing sequence that is designed to seal the wafer from humidity. Chocolate or compound coating is prepared in a separate system where flow behavior must remain constant. The coating is melted and filtered. If real chocolate is used, it is tempered to create stable cocoa butter crystals so it sets with gloss and snap. If a compound coating is used, it is temperature controlled for viscosity and set rate. In either case, viscosity control is critical because it determines coating thickness and whether grooves between fingers fill correctly. Before the main enrobe, many lines apply an undercoat or pre-coat that improves sealing. A thin coat can be applied to the bottom first to reduce moisture migration from the environment into the wafer. The bars then pass through a curtain that coats the top and sides. Excess drains through a wire belt. Air knives remove excess and shape the surface. Air knife settings are tuned to avoid stripping too much coating from corners because exposed wafer edges absorb moisture quickly and lose crispness. If the bar is intended to have fully defined finger lines, the coating flow must not bridge the grooves excessively. Groove definition is managed by coating viscosity, curtain temperature, and belt speed. Too thin a coating leaves exposed edges. Too thick a coating floods grooves and reduces snap separation. The process targets a thickness that seals the wafer while still preserving the break lines. After coating, the bars enter a cooling tunnel. Cooling is staged to set the surface quickly so it does not slump. Then, to crystallize the full thickness without stress. Stable crystallization prevents bloom and keeps the surface firm for wrapping. Tunnel humidity is controlled to prevent condensation because moisture on the surface can cause haze and can also migrate into wafer through microcracks before the coating fully sets. During cooling, the wafer core is also protected from moisture changes. The internal creme acts as a barrier and binds wafer layers, but the wafer will still soften if the coating does not seal fully. The combination of internal creme saturation and external coating seal is what maintains the distinctive, crisp bite. A properly set bar has a rigid, layered core that fractures sharply and a coating that breaks cleanly rather than smearing. Inspection follows cooling. Vision systems check coating coverage, groove definition, and edge exposure. Weight checks confirm stick length and coating mass. Bars with broken fingers or exposed wafer are rejected because they will soften faster and package poorly. Rework handling separates wafer material from coating material because wafer pieces cannot be remelted like coating. Wrapping is designed to maintain a low moisture environment. Bars are fed into flow wrappers that form film around each unit and seal it. Seal integrity matters because moisture ingress softens wafer and destroys snap. Film tension is controlled so it does not scuff the coating or snap fingers. Print registration keeps graphics aligned with the bar orientation. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons. Collation systems handle bars with minimal impact to avoid cracking finger edges. Cartons add protection against compression that would fracture wafers. Cases are packed and palletized. Storage temperature stability keeps coating crystals stable and reduces the risk of bloom and softening. Corny-style cereal bars are manufactured by first engineering a binder that will set at room temperature, then using that binder to lock cereals and inclusions into a compressed slab, then cutting, coating, and wrapping fast enough to preserve crunch and prevent stickiness. The process starts with the binder kettle because everything downstream depends on how that syrup flows, how fast it sets, and how much moisture it brings into the cereal phase. Sugar and glucose syrup are metered into heated tanks and pumped to a cooker. Water is added in controlled quantity because it affects dissolution and final viscosity. If fat is part of the recipe, it is melted separately and held at a stable temperature so it can be injected precisely. If the bar includes honey or malt extracts, those streams are heated just enough to pump without degrading aroma. Cooking raises solids and defines the set behavior. the syrup is heated to dissolve sugars fully and drive off water to a target concentration. Concentration is monitored by temperature and by inline density because the binder must land in a narrow window. Too wet and the finished bar becomes sticky and soft, and it can weep into the wrapper. Too dry and the binder becomes glassy and the bar turns hard and prone to fracture. Residence time is controlled to prevent over-browning because browning changes flavor and also increases viscosity unpredictably. Once the syrup reaches endpoint, it is cooled slightly to a mixing temperature where it will coat dry ingredients without scorching them. This is the moment when flavors and sensitive components are added. Vanilla and fruit aromas are injected late to preserve volatiles. Acid additions are kept minimal and are dosed as solutions when used, because acidity changes inversion rate and can shift stickiness over time. Emulsifiers can be added to keep fat dispersed in the binder and to improve wetting of cereal surfaces. Dry ingredients are prepared in parallel, and their particle size distribution is treated as a structural parameter. Rolled oats are screened to remove fines that would increase dust and create dense patches. Crisped rice or wheat crisps are screened to remove broken fragments because fragments fill voids and reduce crunch. Nuts and seeds are sized to a narrow band, so they distribute evenly and do not punch through the slab. Dried fruit pieces are conditioned to avoid hard clumps because clumps create weak bonding zones and tear during cutting. Chocolate chips or compound drops are stored cool, so they hold shape and do not smear during mixing. Dry blending begins by assembling cereals and inclusions in a low-shear mixer. The mixer is designed to distribute without crushing crisps. Mixing time is short because every extra minute creates more fines by abrasion. The blend is staged in a feed hopper that meters a consistent mass flow into the wet mixing step. Consistent flow is important because binder dosing is tied to dry mass rate. Wet mixing is where the binder and dry blend are joined. The hot binder enters through a manifold that spreads it across the mixer width rather than dumping it in one spot. Paddles fold the dry blend through the binder so every particle is coated. This stage must be fast because the binder is cooling and thickening continuously. If mixing is too slow, the binder sets in patches and leaves dry pockets. If mixing is too aggressive, crisper components break and the bar loses its light texture. Temperature control is the main stabilizer during wet mixing. Binder must be warm enough to flow and coat. It must not be so hot that it softens chocolate drops or makes fruit pieces smear. The dry blend must not be cold enough to shock the binder and cause premature thickening. Many lines temper the dry blend slightly so the combined mass stays within a workable temperature range for forming. Once the mass is uniform, it is delivered immediately to a forming line. Forming begins with depositing the sticky mass onto a moving belt between side rails that define width. A spreader distributes the mass across the belt and a pre-compression roller evens thickness. The mass then passes under a main compression station. Compression is the defining mechanical step for a cereal bar. It determines density, bite, and cut quality. Compression is controlled by roller gap and pressure. A tighter gap yields a denser bar that holds together strongly and cuts with clean edges. A looser gap yields a lighter bar with more visible cereal structure, but can crumble. Compression must also avoid crushing cereal completely. Crushing generates fines that absorb binder and create hard zones. The line tunes compression so the binder bridges particles, while the cereal retains its internal porosity. After compression, the slab enters a setting tunnel or cooling zone. This zone brings the binder through its set transition. If the binder is sugar heavy, it will transition toward a glassy state as it cools, and water activity stabilizes. If the binder includes fats, it will also set as fats crystallize. The tunnel profile is staged so the slab firms gradually. Rapid cooling can create a hard skin while the interior is still warm and mobile, which leads to warp and internal separation. Setting is also where moisture management is locked in. If the binder retains too much moisture, it will migrate into cereal and soften it over time. If it is too dry, it will continue to pull moisture from fruit inclusions and make them tough. The process targets a moisture equilibrium that keeps cereal crisp and fruit pliable. This is achieved by binder solids, fruit conditioning, and tunnel conditions. Cutting follows once the slab reaches a cuttable firmness. Cutting is usually two-stage. A longitudinal cutter trims edges and splits the slab into lanes. A cross cutter then makes bar lengths. Knife selection is important because the slab contains hard inclusions. Dull knives tear the slab and pull cereal out, creating ragged ends. Sharp guillotine blades or rotary knives slice cleanly. Ultrasonic blades can be used to reduce drag through sticky binder and to keep inclusions from catching. Trim is handled carefully because cereal bar trim can be reintroduced only within limits. Trim contains more fines and has different binder distribution. Too much trim increases density and reduces crunch. Rework ratios are therefore controlled so the product remains consistent. After cutting, the bars can be coated or decorated. If the format includes a chocolate base, a tempered or controlled viscosity coating is applied to the bottom. Bars pass over a coating roller that lays down a uniform film. Excess is stripped to a target thickness. A cooling tunnel sets the coating so it does not smear in wrapping. If a drizzle is applied, nozzles deposit lines across the top, while the base is still tacky enough to bond. Nut or crisp toppings can be added during this tack window. Some products include a wafer layer or a milk compound layer. In those cases, the forming line adds that layer either before compression or after cutting. The same principle applies. The additional layer must not introduce moisture that would soften cereal. Adhesion must be strong enough to survive wrapping without delamination. Before packaging, bars pass through final stabilization. This step equalizes temperature so condensation does not occur inside wrappers. It also allows coatings to reach full set and resist scuffing. Bars are then inspected for weight, length, and coating coverage. Broken bars and off-size bars are rejected because they create crumbs and contaminate seals. Packaging is designed around moisture barrier performance because cereal bars lose crunch quickly if they absorb humidity. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are tuned so seals are tight without heating the bar enough to soften binder or melt coatings. Film tension is controlled because excessive tension can crack coatings or deform the bar edges. Coating is applied for traceability. If bars are packed in multi-packs, individually wrapped units are collated and then overwrapped or cartoned. Cartons add crush protection and reduce bending damage. Case packing stacks. Cartons in patterns that limit compression. Storage conditions are controlled so bars do not experience temperature swings that can cause fat bloom on coatings or moisture migration inside the bar. Mars bar manufacture is a timing problem disguised as a candy problem because three materials with very different behavior must arrive at the cutter with the same firmness and then accept a chocolate coat without distortion. The sequence is easiest to understand from the point where the finished bars enter the chocolate curtain. At that moment, the centers must be dry to the touch, straight and dimensionally stable. If they are even slightly warm or soft, the curtain and air knives will round edges and create thin spots. The plant therefore builds the center as a slab, locks its structure by staged cooling, and only then exposes it to chocolate. Chocolate for enrobing is prepared first in process terms because the enrober is sensitive to viscosity drift. Chocolate is melted, filtered, and moved into a tempering loop. Tempering establishes a seed crystal population, so the coating sets fast, with gloss and stable snap. Working temperature is held tightly because small shifts change curtain thickness and final coat weight. The chocolate recirculates through the enrober and is filtered to keep crumbs from building up and roughening the surface. While chocolate is being held ready, the bar center is built upstream as 2 layers. The lower layer is an aerated nougat, and the upper layer is a caramel sheet. These layers are not cooked together because they need different concentration endpoints and different set behavior. Nougat begins with a syrup that defines solids and elasticity. Sugar and glucose syrup are metered and cooked to a specific concentration. The cooker is run to an endpoint that supports a light chew once the mass is aerated. Too high a moisture content produces a soft slab that cannot be cut cleanly. Too low a moisture content produces a tight nougat that loses its light character. The cooked syrup is cooled slightly, so it can be combined with a foam phase without damaging it. The foam phase is produced separately as a protein solution that is aerated under controlled shear. Airflow rate and back pressure are used to fix bubble size distribution. Density is monitored continuously because it becomes the direct knob for bar weight and bite. Fine bubbles are preferred because they resist coalescence and create a uniform interior. Syrup and foam meet in a continuous folding mixer. Folding distributes syrup through the foam while preserving bubble structure. Heat from the syrup strengthens bubble walls and helps lock the microcell network. Fat is injected as a thin stream to soften texture and reduce stickiness. If the nougat is chocolate flavored, cocoa components are introduced in a way that avoids sudden viscosity jumps, often as a pre-dispersed stream rather than dry powder dumped into the foam. The aerated nougat is then deposited as a continuous slab onto a moving belt. A depositor spreads it to width and leveling rollers set thickness. Thickness is controlled tightly because it defines the core height and influences cooling time. Immediately after deposition, the slab enters a cooling tunnel with staged zones. Early zones firm the surface so it can support caramel later. Later zones reduce internal temperature gradually so the slab does not form a brittle skin over a soft interior. Caramel is produced in parallel as an elastic, high solids mass. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach a solids endpoint that yields chew rather than glass. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it can be deposited as a sheet without running. It is held in jacketed tanks with gentle agitation to prevent a surface skin and keep temperature uniform at the depositor. Layering occurs when the nougat slab arrives at the caramel station at the correct firmness. Caramel is applied as a continuous layer using a slot depositor. A smoothing bar spreads the caramel and fixes thickness. The temperature relationship between nougat and caramel is critical. Nougat must not be warm enough to compress under the caramel head. Caramel must not be hot enough to melt the nougat surface. The interface must bond strongly because cutting will pull on it. After caramel deposition, the combined slab is conditioned again. Cooling at this stage is aimed at making the caramel cut stable. If caramel is too warm, it smears and sticks to blades. If too cold, it can crack, especially at the edges. Cooling is staged to avoid differential contraction between nougat and caramel that would create curl. Once the slab reaches the cutting firmness window, it moves into trimming and portioning. Edge trim removes uneven slab edges and creates a uniform width for lane cutting. Trims are handled as rework in controlled ratios because rework carries different temperature history and can change texture if used too heavily. Rotary knives cut the slab into long lanes. A cross cutter then slices lanes into bar lengths. Cutter timing is synchronized to belt speed, so each bar has consistent mass. Knife surfaces are managed to prevent caramel buildup that would tear edges. The cut centers are then separated and aligned for enrobing. Transfer sections are designed with minimal drop height because impacts can dent nougat and shear caramel. Spacing is controlled so bars do not bridge in the chocolate curtain. Many lines apply a brief pre-chill here to firm surfaces and reduce deformation under the curtain. Pre-chill is balanced, so it does not create condensation when the bars enter warmer chocolate zones. Enrobing coats each center with chocolate on top, sides, and bottom. A top curtain covers the bar, and a bottoming system lays a base layer beneath it. Excess chocolate drains through the wire belt. Air knives shape the coating and control the foot. Air knife pressure is tuned so it removes excess without exposing corners, especially where caramel edges can create sharp transitions. If a surface pattern is applied, it is added immediately after the curtain while the coating is still tacky. A stringer deposits thin lines, and then the bars enter the cooling tunnel. Cooling after enrobing is staged to set the chocolate without stress and without bloom. The first zone sets the surface quickly so the coating does not slump and so the bars can be handled. Subsequent zones cool more gradually to promote stable crystal growth. Tunnel humidity is controlled to prevent condensation that would dull the surface. Bars exit at a temperature suitable for wrapping with coating hard enough to resist scuffing. Inspection occurs after cooling. Vision checks look for exposed edges, thin spots, and misshapes. Weight checks verify that cutting and coating remain stable. Rejects are diverted. Chocolate rework is remelted and returned upstream through the tempering loop. Nougat and caramel rework is handled separately because aeration and moisture history affect its behavior. Wrapping begins when the bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is managed so it does not scuff the coating. Coating is applied. Wrapped bars are collated into multi-packs or cartons and case packed. Factories pump out millions of Reese's, Hershey's, and KitKats every single day, using incredible industrial power. Inside these non-stop production lines, molten chocolate and lightning-fast assembly turn raw ingredients into the world's most iconic sweets. In this documentary, we go inside the high-speed world of candy manufacturing to reveal how these legendary treats are made from start to finish. In the massive production facilities where Reese's peanut butter cups are made, the process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's Cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement, is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's Cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. Robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's peanut butter cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs, turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistance to melting at room temperature. Hershey's uses continuous tempering machines, which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. M&M's production begins with the manufacturing of the chocolate core. Each milk chocolate center is formed by molding a precise deposit of tempered chocolate onto a cooling belt. Chocolate mass is created by blending sugar with cocoa liquor and milk solids in a high-capacity mixer. This blend is refined through a 5-roll mill that reduces particle size to below 30 microns. The refined paste is moved to conching tanks where it is mixed and aerated at a temperature of 55 degrees Celsius. Lecithin is added as an emulsifier to achieve a smooth, flowable texture. The conched chocolate is held in jacketed tanks to maintain a liquid state. It is tempered using a 3-stage tempering unit which cycles the chocolate through controlled heating and cooling to form stable crystal structures. Tempered chocolate is pumped to a depositor that releases metered drops onto a stainless steel belt moving through a cooling tunnel. The belt temperature is kept between 5 and 10 degrees Celsius to solidify the chocolate in less than 60 seconds. The formed centers are demolded mechanically and stored in buffer bins before the next process. For peanut M&Ms, the process begins by dry roasting raw peanuts in continuous belt roasters. Roasting temperature is maintained at 160 degrees Celsius for 20 minutes. Peanuts are then cooled by ambient air in a vibrating cooler. After cooling, they pass through a sizing unit that removes undersized or broken nuts. The selected peanuts are fed into panning drums where chocolate is applied in successive layers. Each drum rotates at a fixed angle and speed to ensure uniform tumbling. A measured amount of chocolate is sprayed onto the surface of the peanuts using heated nozzles. After each application, cold air is blown into the drum to partially solidify the layer. This process repeats until the peanuts reach a target diameter. The final chocolate coating is smoothed using a polishing pass with minimal chocolate to eliminate surface irregularities. Crispy M&Ms are built around an extruded rice core. Rice flour and corn grits are mixed with water and processed through a twin-screw extruder. The extruded dough is cut into uniform pellets using a rotating blade. Pellets are puffed in a high-temperature expansion chamber. After expansion, they are dried in a convection dryer, then coated with a thin film of fat to reduce moisture absorption. The puffed cores are enrobed in chocolate using the same panning method applied to peanuts. All chocolate-coated centers are transferred to the sugar coating area. The process starts in large rotating pans where the cores are sprayed with a sugar solution. The sugar syrup consists of sucrose water and glucose and is delivered at a constant temperature of 75 degrees Celsius. Each spray cycle is followed by a drying cycle that circulates dehumidified air around the rotating bed of centers. Sugar builds up in fine layers over dozens of cycles. The panning operator adjusts spray volume drum rotation speed and airflow to maintain uniformity. Once the sugar shell reaches the desired thickness, color is applied. Coloring is done by mixing food dye with shellac and carnauba wax to produce a glossy, tinted coating. The colorant is misted onto the sugar-coated centers in a fine spray. Multiple passes may be required for dark colors like red or brown. After coloring, the coated pieces are polished with a dry mixture of shellac and wax. This step is performed in polishing pans, rotating at low speed. The polishing agent adheres to the surface and is distributed by friction between the tumbling pieces. The resulting finish is smooth, hard, and glossy with highlight reflectivity. Polished M&Ms are discharged from the pans and moved to a conditioning silo. This silo is temperature and humidity controlled to allow the coating to fully harden and stabilize. Residence time in the silo is typically 2 to 4 hours depending on coating thickness. After conditioning, the candies are conveyed to the printing station. The iconic letter is applied using offset graver printers. Each piece is positioned in a dimpled conveyor plate with cavities sized to hold one candy. The plate passes beneath a print head which uses edible white ink. The print roller is engraved with the letter M and rotates in sync with the conveyor. Contact pressure is controlled pneumatically to ensure legibility without damaging the shell. Printed candies are inspected by machine vision systems that detect missing or malformed prints. Unmarked units are removed by air jets and recycled into the system for reprinting. Approved units continue to the packaging stage. The candies are weighed and dosed using multi-head combination weighers that drop exact quantities into vertical form fill seal machines. Packaging film is pulled into the forming collar and sealed into a tube. The bottom is sealed with a heated jaw and the product is dropped in. The top seal is then applied, creating a pillow pack. Filled packages are conveyed to check weighers that verify compliance with weight specifications. Any over or underweight packs are removed automatically. From start to finish, the process involves sequential mechanical operations that include mixing, depositing molding panning, spraying printing, and sealing. Each unit operation is tuned to specific parameters that ensure dimensional consistency and coating integrity. The manufacturing line is modular, with separate zones for chocolate handling, core preparation, sugar coating, and final packaging. Mass flow is maintained using belts, pneumatic conveyors, and elevators that transfer product between levels. The entire line is integrated by a control system that monitors temperature, flow rate, viscosity, and speed at each point. Adjustments are made automatically through feedback loops that maintain constant output. There are no batch holds once the system is running. The chocolate centers flow continuously through coating coloring and packaging without pause. Sugar solutions are replenished through a bulk feed system with inline heating and mixing. Chocolate is tempered in a loop with real-time viscosity monitoring. Each candy undergoes a transformation that begins with a molten mass and ends with a layered composite structure. The core is solid or puffed depending on type. The first layer is tempered chocolate applied by drum enrobing. The second layer is crystalline sugar formed by sequential syrup application and drying. The third layer is colorant and wax forming the glossy finish. The fourth step is marking with the printed letter. All coating is additive applied in micro-thin layers, controlled by time rotation and fluid volume. There is no molding of the outer shape. The spherical form is achieved through cumulative coating and mechanical tumbling. The smoothness is the result of abrasion polishing and repeated layering under rotation. Thermal inputs are limited to chocolate tempering, syrup heating, and ambient conditioning. No baking, frying, or high temperature processing occurs. Moisture is carefully controlled during sugar coating to avoid bloom or crystallization defects. Every part of the process is dry, except the syrup spray and initial chocolate melt. Mechanical design of the panning drums ensures even exposure for each piece. Drum material is stainless steel with ribbed interiors that increase mixing efficiency. Air delivery systems are connected to each drum to maintain controlled drying. The air is filtered, cooled, and dehumidified before being directed at the product. Timing across the system is synchronized by programmable logic controllers. Every depositor, cutter, printer, and packager is indexed to match upstream flow. Any stoppage triggers a cascading halt to preserve continuity. Materials are buffered at key points to allow restart without waste. Twix production begins with controlled preparation of the biscuit base that defines the structure of the bar. Twix biscuit dough is created by feeding wheat flour into a continuous mixing system. The flour is combined with sugar and vegetable fat inside a horizontal mixer. Mixing paddles rotate at low speed to coat flour particles with fat. Water is added in measured flow to bind the mixture into a cohesive dough. Dough temperature is regulated to maintain firmness during shaping. The mixed dough exits the mixer and enters a feed hopper that supplies the forming line. The dough is transferred onto a rolling table, where compression rollers flatten it into a continuous sheet. Roller gap settings determine final biscuit thickness. The sheet passes through alignment guides that maintain straight edges. A rotary cutting drum imprints the dough into uniform rectangular segments. Excess dough is removed and recycled upstream. The shaped dough pieces are placed onto a steel mesh conveyor for baking. The baking stage uses a tunnel oven with multiple heating zones. The conveyor transports dough pieces through gradually increasing temperatures. Initial zones dry the surface without browning. Middle zones promote internal structure development. Final zones create golden coloration and crisp texture. Oven airflow is directed above and below the conveyor. Baking time is adjusted to control moisture content. The baked biscuit bases exit the oven with stable shape and strength. Freshly baked biscuit bases move directly into a cooling tunnel. Ambient and chilled air flow reduces biscuit temperature. Cooling prevents caramel deformation during later stages. Conveyor speed maintains spacing between pieces. The biscuits emerge cooled and rigid. They are aligned into lanes for caramel application. Caramel production occurs in a separate continuous system. Glucose syrup flows into a preheating chamber. Milk solids and sugar are added under agitation. The mixture passes through a vacuum cooker. Reduced pressure lowers boiling temperature. Moisture evaporates rapidly to thicken the caramel. Cooking parameters define final viscosity. The caramel exits the cooker as a smooth, elastic mass. Cooked caramel is transferred into a holding vessel. Slow agitators prevent crystallization. The caramel is pumped through heated pipes to the depositor. The depositor contains multiple nozzles aligned with biscuit lanes. Each nozzle dispenses a precise ribbon of caramel. Deposition rate controls caramel height. Temperature ensures proper flow and adhesion. Caramel-coated biscuits move through a setting tunnel. Cool air partially solidifies the caramel layer. The caramel becomes firm enough to hold shape. The biscuits continue along the conveyor without distortion. The caramel surface remains tacky for chocolate bonding. Chocolate coating begins with preparation of milk chocolate. Cocoa mass, sugar, milk powder, and cocoa butter are blended. The mixture is refined to reduce particle size. Conching develops smooth texture. Finished chocolate is transferred to tempering units. Tempering controls crystal formation. Chocolate reaches a stable liquid state. Tempered chocolate flows into the enrobing machine. A continuous chocolate curtain forms across the conveyor. Biscuit caramel assemblies pass beneath the curtain. Chocolate coats the top and sides evenly. A bottoming system coats the underside through the mesh belt. Excess chocolate drains back into the system. Air knives shape the chocolate layer. Gentle vibration removes bubbles. The coating thickness becomes uniform. Decorative surface lines may form naturally from airflow. The enrobed Twix bars enter a cooling tunnel immediately. Cooling tunnels use staged temperature zones. Initial zones prevent surface cracking. Later zones fully crystallize the chocolate. Air velocity ensures even cooling. Belt speed defines dwell time. The chocolate shell hardens around the biscuit and caramel core. After cooling the bars, exit with rigid structure. The bars are transferred to the splitting station. Twix bars are cut lengthwise into twin fingers. Servo-controlled blades ensure precise separation. Each finger maintains identical dimensions. Separated Twix fingers are aligned on packaging conveyors. Spacing belts organize the flow. The bars enter flow wrapping machines. Packaging film is fed from large rolls. The film wraps around each finger. Longitudinal seals are formed by heated rollers. End seals are created by rotating jaws. Wrapped fingers are paired for twin pack format. Collation belts bring two wrapped fingers together. The paired unit is wrapped again or inserted into an outer sleeve. Wrapping speed matches upstream production. The sealed packs exit the line in continuous flow. Throughout Twix, manufacturing every step is synchronized. Conveyor speeds coordinate with deposition rates. Thermal stages are sequenced to avoid overlap. Mechanical forming ensures consistent geometry. Material flow remains uninterrupted from dough to wrapper. The biscuit base provides rigidity. The caramel supplies chew and adhesion. The chocolate delivers coating and protection. Each layer is applied in a defined order. Temperature control maintains layer integrity. Timing ensures bonding without deformation. Twix production operates as a linear system. Dough shaping precedes baking. Baking precedes caramel deposition. Caramel setting precedes chocolate enrobing. Chocolate cooling precedes cutting and wrapping. Each stage depends on the previous one. Ingredient transformations are mechanical and thermal. Dough changes through heat exposure. Caramel thickens through evaporation. Chocolate crystallizes through controlled cooling. No stage reverses a previous transformation. The biscuit sheet thickness defines bite texture. Caramel viscosity defines chew resistance. Chocolate thickness defines snap. These variables are adjusted through machine settings. No manual shaping occurs after initial dough forming. Continuous monitoring of belt alignment prevents product drift. Sensors maintain spacing accuracy. Pump pressures control flow stability. Roller speeds define forming precision. Each parameter is linked to output consistency. Twix bars emerge fully assembled before packaging. the layered structure remains intact. The product shape remains constant across units. The manufacturing line produces thousands of bars per hour. Output remains uniform due to synchronized automation. Every Twix bar follows the same physical path. Raw materials enter as powders and liquids. Finished bars exit as layered chocolate products. The process relies on controlled movement. Thermal transitions define each stage. Mechanical handling preserves structure. Snickers bars are built in layers, starting with the nougat foundation. The nougat is produced by combining sugar, corn syrup, and milk powder in a heated mixing vessel. These ingredients are blended and cooked until they form a thick paste. A separate stream of whipped egg whites is prepared using high-speed beaters. The aerated egg white mass is gradually folded into the hot sugar mixture. This step introduces air cells and creates the spongy texture of the nougat. The blending continues until the mixture reaches uniform density and viscosity. The final nougat mass is held in a feed tank equipped with slow paddles to prevent collapse. The nougat is deposited as a continuous slab onto a moving belt. The belt is lined with a non-stick material to allow clean release. A leveling roller spreads the nougat to the target height. Guide rails control the slab width. The slab is conveyed into a cooling chamber to set the structure. Chilled air circulates around the slab until surface temperature drops below 15 degrees Celsius. The cooled nougat slab exits the chamber with a firm texture and is ready for the next layer. Caramel is prepared in a separate cooking line using glucose syrup, milk fat, and sucrose. These ingredients are fed into a continuous cooker with steam-heated zones. The mixture is heated to reduce water content and initiate Maillard reactions. Caramelization develops flavor and viscosity. The cooked caramel exits the vacuum chamber and enters a holding tank. The tank is agitated slowly to maintain homogeneity and prevent crystallization. The caramel temperature is maintained near 60 degrees Celsius for optimal flow. Roasted peanuts are prepared separately. Raw peanuts are roasted in a forced air roaster where temperature is held between 160 and 180 degrees Celsius. Roasting continues for 20 minutes until internal moisture falls below 2%. The peanuts are cooled by ambient air, then passed through a vibrating grater. Oversized and broken peanuts are removed. The accepted peanuts are stored in silos connected to the deposition system. Caramel is deposited onto the cooled nougat slab using a curtain-style applicator. The applicator spans the full width of the slab and releases caramel in a uniform layer. Flow rate and belt speed are adjusted to control caramel thickness. Directly after caramel application, roasted peanuts are dropped from a vibratory feeder. The feeder spans the same width as the slab. A controlled quantity of peanuts is dispensed and embedded into the caramel by a light compression roller. This roller presses the nuts into the surface to ensure mechanical bonding. The multi-layer slab is conveyed through a second cooling tunnel. The tunnel has temperature zones starting at 12 degrees Celsius and ending at 6 degrees Celsius. Chilled air is circulated above and below the belt to harden the caramel. Dwell time is calibrated to match the slab thickness and maintain shape stability. The slab exits the tunnel with a cohesive structure and defined layers. A guillotine cutter slices the multi-layer slab into narrow lanes. The cutter uses servo-controlled blades aligned with the slab width. The lanes are transferred onto narrower belts for portioning. Another guillotine cuts the lanes into bar-length segments. Blade speed and belt speed are synchronized to ensure uniform bar size. Each segment is now a complete core containing nougat, caramel, and peanuts. The bar cores are spaced and oriented for enrobing. They enter the chocolate coating system in a single file. Milk chocolate is melted in a jacketed tank and tempered in a continuous flow unit. The tempering process includes heating to melt all crystals, cooling to initiate stable crystal formation, and reheating to a precise working temperature. The tempered chocolate flows into a pump system that feeds the enrober. Each bar passes under a chocolate curtain that coats the top and sides. The base of each bar contacts a chocolate-coated roller or is sprayed from below. Chocolate flow is adjusted by modifying pump speed and curtain width. Excess chocolate is removed by a vibrating section that shakes the belt gently. Air knives apply a controlled stream of air to smooth the surface and reduce buildup. The coated bars enter a cooling tunnel to crystallize the chocolate. The tunnel has multiple zones with decreasing temperatures. Airflow is directed to maintain even cooling without condensation. The bars are conveyed for a fixed duration to complete the chocolate setting process. The final chocolate shell is solidified and stable upon exit. Each Snickers bar is now fully assembled and coated. Bars are aligned for wrapping using guiding rails and spacing conveyors. Flow wrappers are fed with printed film from a reel. The film is shaped into a tube around each bar. Heat sealing rollers create the longitudinal seam. Rotating jaws apply end seals. Seal pressure and temperature are monitored to match film type. The wrapped bars are conveyed into collection bins or directly to packing systems. Depending on product format, bars may be grouped into single, twin, or multi-pack configurations. Grouping conveyors align the bars into sets. Mechanical pushers or robotic arms load the grouped bars into cartons. Cartons are formed from flat blanks and glued using hot melt adhesive. Cartons are closed and sealed at the final station. No manual intervention is used during shaping, layering, cutting, or wrapping. All movements are performed by synchronized mechanical systems. Sensors monitor product position and spacing. Feedback loops adjust flow parameters. Each bar follows the same linear path from ingredient feed to final wrap. Nougat provides internal volume and structural support. Caramel binds the peanuts and delivers chew. Peanuts create inclusion texture and flavor variation. Chocolate forms an outer shell that locks the layers in place. Each component is manufactured and applied in discrete steps. Thermal and mechanical conditions are optimized for each transition. The slab format enables high-speed processing. Layering occurs in continuous motion. Cooling is integrated between each stage to preserve geometry. Cutting is servo-synchronized to belt speed. Chocolate tempering is calibrated to match bar throughput. Wrapping systems operate at matched cadence to upstream enrobing. Ingredient flow is regulated by volumetric pumps, gravity feeders, and temperature-controlled tanks. Mixing occurs in closed vessels with integrated agitators. Heat is applied via indirect steam or electric jackets. Each process vessel is isolated by flow valves and sensors. Conveyor systems link every step of the process. Belt widths and speeds are chosen to prevent jamming and maintain alignment. Transfer points are angled to reduce impact and preserve bar shape. Side guides and rollers keep products centered. Accumulation zones provide buffer capacity between stages. The system supports continuous operation without backtracking. Each bar is formed from base to wrap in a single direction. Mechanical shaping precedes deposition. Deposition precedes cutting. Cutting precedes coating. Coating precedes cooling. Cooling precedes wrapping. Every phase transforms material by specific mechanical or thermal means. Mixing combines dry and wet. Cooking removes water. Depositing creates form. Cooling fixes structure. Cutting defines unit size. Enrobing applies the shell. Wrapping seals the finished form. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the cream filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. Cadbury Dairy Milk is manufactured by transforming milk and sugar and cocoa into a low-moisture chocolate crumb or chocolate mass, refining it into a smooth suspension, conching it to stabilize flow, tempering it to lock stable cocoa butter crystals, then molding and packing while temperature and viscosity stay tightly controlled. Milk handling is treated as a structural step rather than a flavor step because dairy solids determine body and sweetness balance. Milk can enter as liquid milk, concentrated milk, or milk powder depending on plant design. Liquid streams are filtered and held at controlled temperature for predictable pumping. Powder streams are sieved to remove clods because clods do not hydrate evenly and later create texture specks. Sugar is screened to control crystal size and to remove lumps that would resist refining. Cocoa components are prepared as cocoa liquor and cocoa butter streams held warm so they remain pumpable. Cocoa powder streams are sifted when used to remove compaction lumps. All dry ingredients are kept low in moisture because water in chocolate causes thickening and unstable flow. A key feature of many milk chocolate lines in this style is crumb production, which converts milk and sugar into a dry solid that carries developed dairy notes and improves process stability. Crumb production starts by combining milk and sugar in a cooker. The mixture is heated while being mixed, so sugar dissolves and water begins to evaporate. Heating is controlled to drive off water without scorching milk solids. As water leaves, the mixture becomes thicker and begins to form granular solids. The cook continues until the mass becomes a dry or semi-dry crumb with low residual moisture. During crumb cooking, thermal history is tightly managed because it controls flavor development and functional behavior. Too gentle a cook leaves high moisture and produces crumb that later thickens the chocolate unpredictably. Too aggressive a cook darkens sugars and drives strong cooked notes that can overwhelm the profile. The endpoint is set by moisture content, and by the way, the crumb fractures when broken. When the endpoint is reached, the crumb is cooled and milled into a manageable size so it can be blended uniformly later. Cocoa liquor and cocoa butter are prepared in parallel. Cocoa liquor is held warm so it stays fluid and is filtered to remove solid lumps. Cocoa butter is melted in jacketed tanks and filtered for clean metering. These fat streams define the continuous phase of the final chocolate, and they also control viscosity through the downstream steps. Mixing combines crumb with cocoa liquor, cocoa butter, and additional sugar or milk solids as required by the recipe. The goal is to create a homogeneous pre-mass where solids are evenly distributed in fat. Mixing is done in high-torque mixers with wall scraping because the mass can be thick before refining. The mixture transitions into a paste with consistent color and no dry pockets. At this stage, the mass is not yet smooth. Sugar crystals and crumb particles are still large enough to be detected on the tongue. Refining is performed to reduce particle size. The pre-mass is fed to roll refiners or other milling systems. In roll refining, the mass passes through a series of rolls with decreasing gaps. Each pass squeezes and shears particles smaller. The refined output leaves the last roll as a thin film that breaks into flakes. These flakes have high surface area and must be processed into conching quickly to prevent moisture pickup. Conching is the step that transforms refined flakes into a smooth flowing chocolate with stable flavor. The flakes enter a conche where mechanical work coats each particle with fat and breaks down remaining agglomerates. Heat keeps cocoa butter fluid and supports moisture removal. Airflow through the conche carries away moisture and volatile compounds. Moisture removal is essential because even small amounts of water cause chocolate to seize and become thick. Conching also stabilizes rheology by reducing friction between particles. Early in conching, the mass can be dry and pasty. As fat distribution improves, the mass becomes smoother and viscosity drops. The concha profile is tuned to reach a target viscosity for molding and enrobing while maintaining the desired flavor. Over-conching can reduce throughput and strip some volatile character. Under-conching leaves high viscosity and inconsistent snap. Emulsifiers are typically added near the end of conching. Lecithin improves particle wetting and reduces yield stress. Another flow modifier can be used to reduce viscosity further at a given fat level. These additives are dosed precisely because small changes alter how chocolate behaves in deposit heads and tempering machines. The chocolate is then filtered and transferred to holding tanks with gentle agitation to keep the suspension uniform. Tempering is the controlled crystallization of cocoa butter that gives dairy milk its stable set and gloss. Chocolate is first heated to melt existing crystals fully. It is then cooled under agitation so new crystals form. It is then reheated slightly to melt unstable forms while keeping stable seed crystals. The output chocolate contains a controlled population of stable crystals and remains fluid at the working temperature. Temper is monitored continuously because it drives mold release and surface quality. If temper is too low, the chocolate sets slowly and releases poorly and can bloom later. If temper is too high, viscosity rises and the chocolate becomes thick, causing poor mold, fill and thick edges. Tempering machines adjust cooling and heating in small increments to maintain the target crystal content. Molding shapes the chocolate into bars and blocks. Polycarbonate molds are cleaned and pre-warmed to prevent condensation. Depositors meter chocolate into each cavity with tight mass control. The filled molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also improves detail in any embossed features. Cooling tunnels set the molded chocolate. Cooling is staged to set the surface quickly without creating internal stress. The chocolate contracts slightly as it cools, which helps demolding. If cooling is too fast, the chocolate can crack or warp. If too slow, the line speed drops and molds remain occupied. Cooling also must avoid condensation because moisture on the surface can cause sugar bloom. After cooling, the molds are inverted and the bars release. Release depends on correct temper and correct cooling because the bar must contract away from the mold wall. Bars transfer to conveyors where they are inspected for surface defects. Weight checks confirm deposit accuracy. Bars with defects are diverted for rework. Rework is remelted and returned upstream in controlled ratios so it does not destabilize tempering. If the product includes inclusions or filled formats, the molding stage expands. Inclusions, such as nuts, are screened and kept dry. They can be placed into molds before chocolate deposition or blended into chocolate with controlled suspension. Filled formats use sequential depositing. A shell is deposited and partially set. A filling is dosed and then sealed with a chocolate back layer. Cooling profiles are adjusted because fillings change heat transfer and can insulate. After demolding, bars move to wrapping. Wrapping protects chocolate from oxygen, moisture, and abrasion. Bars are indexed into wrapping machines that fold foil or film around each bar. Fold geometry is controlled so edges are crisp and seals are tight. If an inner foil and outer paper wrap are used, the foil provides the barrier and the paper provides stiffness and print. Heat sealing or crimping forms the closure, depending on wrap type. Coded information is applied during wrapping or immediately after. Vision systems check wrapper alignment and seal integrity. Check weighers verify pack weight. Wrapped bars are then collated into cartons if needed. Cartons are erected and filled with a defined count. Cartons are closed and glued. Finished units are case-packed and palletized. The process control backbone for dairy milk is moisture management and particle size management and crystal state management. Crumb production drives moisture down and creates a stable dairy sugar matrix. Refining drives particle size down for smoothness. Conching drives off remaining moisture and stabilizes flow by coating particles with fat. Tempering builds the correct crystal population for gloss and snap and clean mold release. Cooling locks the structure and wrapping protects it from temperature swings and humidity. Three Musketeers is manufactured by producing a highly aerated chocolate-flavored nougat center, forming it into a continuous slab, cutting it into bars, enrobing those bars in tempered chocolate, then cooling and wrapping while density and coating thickness remain tightly controlled. The defining step is the aeration system, because the bar's texture depends on holding a large volume of fine bubbles inside a stable sugar and fat matrix. The process, therefore, starts by building two streams that can be combined without collapsing air cells. One stream is a cooked syrup with a precise solids level. The other stream is a foamed phase that carries air at a controlled density. Syrup preparation begins with sugar and glucose syrup metering. granulated sugar is screened to remove clumps and to keep dissolution predictable. Glucose syrup is held in jacketed tanks so it pumps at stable viscosity. Water is filtered and tempered because inlet temperature affects dissolving rate and cooker stability. The streams enter a dissolver where agitation produces a clear solution. Strainers remove any undissolved grains because grains concede crystallization and create a gritty center. The clear syrup then enters a continuous cooker where heat drives off water. Many systems heat under pressure, so temperature can rise quickly without boiling in the coil. After the heating zone, the syrup may enter a flash stage where pressure drops and water vapor leaves rapidly. This trims moisture to the target. Moisture control here sets final nougat resilience. Too much moisture yields a soft center that can deform under cutters. Too little moisture yields a tough center that loses its light bite. While the syrup is being cooked, the aerated phase is prepared. A protein solution is mixed to a defined concentration and then sent to a continuous aerator. Airflow and rotor speed are controlled to create small bubbles and stable foam. Foam density is monitored continuously because it is the most direct indicator of final bar lightness. The foam must be stable enough to survive contact with hot syrup. It must also be fine enough to produce a smooth bite rather than large voids. The cooked syrup is cooled slightly to a controlled blending temperature and then combined with the foam in a continuous mixer. The mixer is designed to fold the streams together rather than whip. Folding distributes syrup through the foam while preserving the bubble structure. The syrup heat partially sets the protein films around bubbles and locks in the microcell network. Chocolate flavor is built into the nougat by adding cocoa components and sometimes chocolate liquor or cocoa powders at controlled points. These additions must be dispersed without deflating the foam. They can be introduced as fine powders, pre-blended with part of the syrup, or as a liquid chocolate. Stream introduced downstream of the highest shear zone. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be added in small doses to improve stability and control viscosity. Once mixed, the aerated nougat exits as a warm plastic mass with controlled density and viscosity. It is deposited onto a moving belt as a continuous slab. A spreader head lays down the slab at a defined width. Gauge rollers and leveling bars set thickness. Thickness control is critical because it determines bar mass and also affects cooling time. The slab enters a cooling tunnel where temperature drops in stages. Staged cooling prevents a hard skin from forming over a warm interior because that skin can crack and create weak planes during cutting. As the slab cools, the bubble structure stabilizes further. Fat begins to crystallize, and the nougat transitions from plastic to firm yet compressible. The target firmness is set, so the slab can be cut cleanly without smearing. If the slab is too warm, knives drag and deform edges. If too cold, the slab can fracture at the surface and create rough edges that show through the chocolate coat. Edge trimming is often used to remove uneven slab edges. Trims are collected as controlled rework. Rework must be managed carefully because aerated material behaves differently than fresh mix. Excess rework can shift density and bubble size distribution. The main slab then moves into lane cutting. Rotary knives slice the slab into long ropes of constant width. A crosscutter then slices the ropes into bar lengths. Cutter timing is synchronized with belt speed, so each bar length is consistent. The cut centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between bars. Transfer points are designed with low drops and soft transitions because aerated centers dent easily. Some lines include a brief pre-chill to firm the surface. Firmer surfaces accept chocolate more evenly and reduce deformation as the center passes through the curtain. Chocolate coating is prepared in a separate system where temper is the key variable. Chocolate is melted and filtered to remove unmelted particles. Tempering then creates stable seed crystals by controlled cooling and reheating. Working temperature is set so viscosity remains stable at the curtain. Viscosity controls the thickness of the coating and therefore the final chocolate to center ratio. Enrobing coats the bar with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a roller or a bath section that lays a consistent base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot at the base. Air knife settings are tuned to remove excess without exposing corners. Because the center is soft, air knife force is balanced so it does not deform the nougat under the coat. A pattern top can be applied by a stringer that drizzles thin chocolate lines over the wet surface. The drizzle must bond before the base coat fully sets. This requires a precise timing window between curtain exit and cooling tunnel entry. Pattern flow rate and nozzle spacing are synchronized with belt speed. Cooling tunnels set the chocolate. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Cooling must avoid condensation because moisture on chocolate creates sugar bloom and dullness. Tunnel humidity is controlled, and the bar exit temperature is set to support wrapping without scuffing. During cooling, the nougat center also equilibrates. The fat phase in the center continues crystallizing, and the bubble walls become more rigid. The center remains light and compressible, but it gains enough strength that handling pressure from wrappers does not deform it. The chocolate coat becomes a barrier that reduces moisture exchange and helps maintain texture over shelf life. Inspection follows cooling. Vision systems check for exposed edges and coating voids. Weight checks confirm bar mass and coating mass. Bars outside tolerance are diverted. Diverted product is handled as rework streams that are remelted for chocolate or reprocessed for nougat according to process rules. Wrapping begins once the bars reach a stable temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are controlled, so seals are tight without shrinking film onto the bar. Film tension is controlled to avoid scuffing the chocolate surface. Print registration aligns graphics to bar position. Coating adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Twix bars are manufactured by producing a crisp biscuit finger, applying a controlled caramel layer, enrobing the assembled sticks in tempered chocolate, then cooling and wrapping while moisture and viscosity remain tightly controlled. The process begins with the biscuit line because the biscuit defines the bar geometry and the snap that must survive caramel deposition and chocolate coating. Flour is sieved to remove lumps and to standardize flow. Sugar is screened so crystal size is consistent and does not tear dough during mixing. Fat is conditioned to a plastic state so it blends evenly and limits gluten development. Leavening salts are weighed precisely because they determine porosity and bite strength. Water and any dairy liquids are tempered because dough temperature controls how cleanly it sheets and cuts. Mixing is designed to create a short dough with limited gluten. Fat and sugar are first blended to distribute fat and reduce dry friction. If a creaming step is used, it is controlled to avoid excessive air because too much air weakens biscuit and increases breakage during handling. Dry ingredients are then introduced and mixed only until the dough becomes cohesive. Minimal mixing limits gluten formation and preserves a tender, crisp structure rather than a tough one. Dough conditioning follows. The dough rests so moisture equilibrates and the dough relaxes. Relaxation prevents snapback during sheeting. Dough temperature is held in a narrow range, so fat stays plastic. Warm dough smears on rollers. Cold dough cracks at edges and produces rough cutouts. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through reduction rollers that gradually thin it. Gauge rollers set final thickness tightly because thickness drives bake time and final snap. Dusting flour can be applied sparingly to prevent sticking, but excess dust is avoided because it burns and creates specks. The sheet enters rotary cutting and docking. Rotary cutters punch long biscuit fingers. Docking pins create small holes through the dough. These holes vent steam during baking and prevent blistering and warping. The cut fingers transfer to an oven band. Scrap dough around the cutouts is lifted and recycled. Scrap ratio is controlled because repeated working increases gluten and changes dough behavior. Baking occurs in a tunnel oven with staged zones. Early zones set the shape as fat melts and moisture begins to leave. Leavening gases expand and create small pores. Mid-zones drive moisture down and develop a light golden color. Later zones finish drying so the biscuit reaches a low moisture endpoint. Moisture endpoint is critical because the biscuit must remain crisp under caramel and chocolate. If moisture remains too high, the biscuit will soften and lose snap. If moisture is too low, the biscuit becomes overly brittle and breaks during sandwiching and wrapping. After baking, the biscuit fingers exit the oven and enter cooling. Cooling stabilizes structure as fats resolidify. Cooling air is controlled and often dehumidified because dry biscuits can absorb moisture from humid air. The goal is a consistent exit temperature and moisture level. The cooled fingers are then aligned into lanes for caramel application. Caramel production runs in parallel because caramel must be depositable and stable. Sugar and glucose syrup are cooked with milk components to develop caramel flavor and reach an elastic solids endpoint. The cook drives off water until the caramel will hold shape at room temperature. Fat is added to smooth the caramel and reduce tack. The endpoint is set so the caramel bites cleanly without becoming glassy. Overcooked caramel becomes hard and can fracture when the bar is bitten. Undercooked caramel flows and smears in packaging. Caramel is cooled from cook temperature to a working temperature where viscosity is stable for deposition. It is held in jacketed tanks with gentle agitation to prevent skin formation. Pipes to the depositor are heated to prevent cold plugs. Viscosity is monitored indirectly by pressure and flow because a small temperature drift changes deposit weight and layer thickness. Caramel deposition applies a continuous layer onto the biscuit fingers. A slot depositor or multi-nozzle head lays caramel onto the moving biscuit lane. A leveling bar smooths the surface and sets thickness. Thickness must be uniform because it influences bite and chocolate coverage. If caramel is too thick, it can squeeze out under chocolate and create uneven edges. If too thin, the bar loses the intended caramel to biscuit balance. The biscuit temperature at deposition is controlled. Biscuit must be cool enough to remain crisp and to avoid melting caramel into the pores too deeply. It must not be so cold that caramel fails to bond. The line targets a temperature window where caramel adheres but does not soak. After deposition, the caramel-topped fingers pass through a cooling tunnel to set the caramel surface. Cooling must be staged so the surface firms without cracking. A firm surface is required before enrobing so caramel does not smear on belts. Once the caramel is set, the sticks are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfers minimize drop height because biscuit can crack and caramel can shear. The sticks may pass through a brief pre-chill to firm surfaces and improve chocolate flow behavior. Chocolate preparation is a separate stream where temper control is essential. Chocolate is melted and filtered. It is tempered to create stable cocoa butter seed crystals. Working temperature is set to maintain consistent viscosity. Viscosity determines how thick the chocolate curtain is and how much chocolate remains after air knife trimming. Enrobing coats the sticks in chocolate. A top curtain covers the caramel and sides. A bottoming system coats the underside so the biscuit is sealed. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot thickness. Air knife settings must be tuned because too much air can expose corners, especially at biscuit edges. Too little air leaves thick feet that can crack during cooling. If a top pattern is required, it is applied immediately after the main curtain. A stringer deposits thin chocolate lines across the surface, while the base coat is still wet enough to bond. The stick then enters the cooling tunnel. Cooling sets the chocolate and locks the finished structure. The first zone sets the surface quickly to prevent slumping. Later zones cool gradually to promote stable crystal growth and reduce bloom risk. Cooling also reduces the internal temperature of caramel so it reaches its final elasticity. The exit temperature is set so the chocolate is hard enough for wrapping without scuffing. After cooling, the bars are inspected. Vision systems detect exposed biscuit corners and coating voids. Weight checks confirm portion control. Defective bars are rejected. Rework chocolate is remelted and returned upstream, while biscuit and caramel rework is handled separately because it carries moisture and texture changes. Wrapping begins with feeding bars into flow wrappers. Film is formed around each bar and sealed. Seal temperature and dwell are controlled so seals are strong without overheating the chocolate. Film tension is controlled to prevent scuffing. Print registration aligns graphics. Coding adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft-style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or Sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity and by torque and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. Gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the R sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed, so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further. Extrusion requires dough with consistent viscosity. Viscosity is controlled by water level and fat plasticity. Formed pieces are transferred onto baking bands or trays. Transfer must avoid deformation. Conveyors use gentle acceleration and minimal drop heights. Spacing is controlled because pieces can spread or expand slightly during baking. If pieces are too close, they can merge. Baking is the main transformation stage. Biscuits enter a tunnel oven with multiple heat zones. Early zones apply heat that sets surface structure. Fat melts and the dough begins to relax. Water begins to evaporate and steam forms within the piece. Leavening reacts and produces gas that creates internal porosity. As baking continues, starch gelatinizes, then dries into a rigid matrix. proteins coagulate and contribute to structure. Sugar dissolves in the early wet phase and then participates in browning reactions as moisture falls. Maillard reactions and caramelization develop color and flavor. Oven temperature and airflow control the rate of these reactions. Moisture endpoint is a primary target because it defines crispness and shelf stability. For crisp biscuits, the line drives moisture low so the biscuit fractures cleanly. For softer biscuits, the line stops earlier to retain more moisture. Moisture control is managed by oven profile and by piece thickness. A thicker biscuit needs longer bake or higher heat. A thinner biscuit can overbrown quickly if heat is too high. Airflow influences drying and surface texture. Strong convection removes moisture fast and yields a drier surface. Gentler airflow allows more, even internal drying. Many ovens use independent top and bottom heat control. Bottom heat drives structure set from the band side. Top heat drives surface color. Balancing top and bottom heat prevents warping and ensures even bake. Spread and shrink are managed through dough formulation and early oven conditions. If early heat is low, the dough can spread too much before setting. If early heat is high, the surface sets quickly and limits spread. The line adjusts the first oven zone to tune diameter and thickness. After baking the biscuits, exit hot and fragile. They move to cooling conveyors where they firm as fats, resolidify. Cooling also allows moisture to redistribute slightly. For crisp biscuits, cooling air is often dehumidified because biscuits can absorb moisture from humid air and lose snap. Cooling is staged, so thermal stress does not crack the biscuits. During cooling, the biscuits are inspected and sorted. Vision systems can detect overbaked color and broken pieces and misshapes. Metal detection can be placed after cooling. Crumb removal systems collect loose fragments that would contaminate packaging seals. If the product includes surface toppings such as sugar crystals or salt or glaze, the application is timed to surface condition. Sugar sanding is often applied before baking so crystals embed and partially melt. Glaze can be applied after baking and then dried lightly. These steps require separate dosing systems and add additional moisture management considerations. Packaging is designed to protect biscuits from moisture and breakage. Biscuits are collated into stacks and oriented. Stacking systems use lanes and pushers to form uniform packs. The packs are then flow wrapped or placed into trays. Flow wrapping uses barrier film that blocks water vapor. Tray packs provide mechanical support and reduce breakage during transport. Seals must be clean because crumbs can interfere with seal integrity. Packaging machines use crumb extraction near the seal jaws. Film tension and seal temperature and dwell time are controlled, so seals are tight. Coating is applied for traceability. Check weighers confirm count or weight. Oat bars are manufactured by converting oats and binders into a cohesive slab, setting that slab by baking or cooling, then cutting it, and packaging so texture and moisture stay within a tight window. Production starts with oat preparation because particle size distribution controls chew and structural strength. Rolled oats are screened to remove fines and oversized flakes. Fines create dust and can make bars dense and crumbly. Oversized flakes create weak points and poor cut edges. If the product uses oat flour or milled oats, that stream is prepared separately and sieved to prevent clumps. Nuts, seeds, or crisp inclusions are sized and cleaned so they do not introduce hard fragments that damage cutters. Sweetener and binder streams are prepared in parallel. Glucose syrup or similar syrups are held in jacketed tanks to maintain a stable viscosity for pumping. Sugar can be added as granulated crystals or dissolved into a syrup depending on the texture target. Fat sources such as vegetable oil or butter are melted and held at controlled temperature. If nut butters are used, they are warmed to a flowable state and mixed to eliminate oil separation. Emulsifiers can be staged to stabilize the binder and improve coating of dry particles. Dry minor ingredients are pre-blended to ensure uniform distribution. Salt is weighed and dispersed to prevent salty pockets. Leavening is used only in certain baked styles, and it is weighed precisely. Protein powders or milk powders are sieved because they form lumps when exposed to binder. Spices and flavors are blended into the dry premix or injected into the binder depending on volatility. The process creates a binder first because the binder must coat every dry particle quickly. A heated mixing kettle combines syrups and sugars and fats. Agitation keeps the mixture homogeneous and prevents hot spots. Temperature is raised to dissolve sugar if needed and to reach a target solids level. Solids level controls final stickiness and water activity. If solids are too low, the bars remain sticky and can weep. If solids are too high, the binder becomes glassy and the bar becomes hard. Cooking is used in many oat bar lines to adjust binder concentration. The binder is heated to drive off water and to raise viscosity. Time and temperature are controlled because overheating darkens sugars and changes flavor. When the binder reaches target viscosity, it is cooled slightly to a mixing temperature that will not damage heat-sensitive inclusions. Cooling also prevents excessive softening of oats during mixing. Flavor addition often occurs after this cooling step. Vanilla and spice extracts are injected, so aromatics are preserved. If fruit concentrates are used, they are blended in at controlled temperature because they can burn or separate when overheated. Acidulants can be added to balance sweetness and also to manage microbial stability. The binder is mixed until it is uniform and then it is pumped to the forming line. Dry blending begins with oats as the primary structural phase. Oats are loaded into a ribbon blender or a paddle mixer. The mixer runs at low speed to avoid breaking flakes. If nuts or seeds are included, they are added and distributed. Dry powders, such as protein, are added as a pre-mix to reduce streaks. The dry blend is mixed only until distribution is uniform because overmixing generates fines. Binder is then introduced into the dry blend. The binder is metered by mass flow, so the ratio remains stable. It is delivered through spray bars or a manifold that distributes it across the mixer width. The mixer switches to a folding action that turns the dry blend through the binder stream. The goal is rapid coating without crushing inclusions. Coating uniformity is critical because uncoated oats fall apart and overcoated zones become sticky clumps. Mixing endpoint is judged by appearance and by torque. The mass should look uniformly glossy with no dry pockets. It should flow as a cohesive mixture but still show discrete oat flakes. If the mass is too wet, it will smear during forming and create dense bars. If it is too dry, it will not bind and will shed crumbs during cutting. Temperature during mixing is monitored because warm mass flows better but can collapse structure later. Once mixed, the mass is transferred to a forming system that creates a continuous slab. Transfer chutes are designed to reduce segregation because heavier inclusions can settle. Many lines use a short transfer distance and a low drop height. The mass is fed onto a moving belt through a spreader that distributes it to full width. The spreader uses leveling bars and rotating paddles to create an even bed height. Compaction follows spreading and it defines bar density. A set of compression rollers presses the mass to a target thickness. Roller pressure and gap determine final thickness and porosity. Higher compression yields a dense bar with fewer voids and a cleaner cut. Lower compression yields a lighter bar with more chew and visible structure. Compression must be uniform across the belt to avoid thickness variation. If the product includes a base layer such as chocolate or yogurt coating, the sequence can include a bottoming step. A thin film is applied to the belt and partially set before the oat mass is deposited. This creates a bonded base that can act as a moisture barrier. The base layer thickness must be controlled because it affects cutting and packaging. Setting the slab depends on product style. For baked oat bars, the slab enters a tunnel oven. Baking drives off moisture and sets structure by solidifying sugars and fats. Oven zones are tuned to avoid overbrowning while reaching a target moisture endpoint. Airflow and temperature control surface drying and internal set. The slab must be firm enough to cut cleanly, but not so dry that it becomes brittle. For no bake oat bar setting is achieved by cooling rather than baking. The slab enters a cooling tunnel where fats crystallize and binders firm. Cooling profile is staged to prevent cracking. Rapid surface cooling can create a hard skin while the core remains soft. A staged profile cools evenly and yields a uniform firmness for cutting. Moisture control is critical in both styles. Oat bars sit in a moisture window where they are not sticky but still chewy. Too much moisture leads to stickiness and microbial risk. Too little moisture leads to hardness and crumbling. The process controls this window through binder solids and oven time or cooling time. Water activity is measured on samples and used to adjust settings. After baking or cooling, the slab may be conditioned before cutting. Conditioning allows temperature and moisture to equalize across the slab thickness. This reduces internal stress and prevents edge cracking. Conditioning also stabilizes the surface so blades do not drag. For baked slabs, conditioning can include a short cooling stage to bring the slab to a consistent cut temperature. Cutting converts the continuous slab into bars with defined weight. A first cutter trims the edges because edges can be uneven from spreading. Trim is collected for rework depending on recipe constraints. The main slab then passes through a guillotine cutter that creates long strips. A cross cutter then divides strips into bar lengths. Blade speed and sharpness are tuned to avoid tearing oats. Warm slabs can smear and stick to blades. Cold slabs can fracture and generate crumbs. If the product includes a top drizzle or enrobing, the coating step can occur after cutting. Chocolate is tempered and then applied as a curtain or as a drizzle. Drizzle heads deposit controlled lines. Enrobing coats the bottom or full bar. Coatings are then set in a cooling tunnel. Coating application must avoid adding excessive heat that softens the bar matrix. Cadbury chocolate begins as a controlled blend of cocoa components, dairy components, sugar, and fat that is refined into a smooth suspension, conched to stabilize flow and flavor, tempered to lock in stable crystals, then molded and packed, while temperature and viscosity stay inside a narrow window. Production starts with cocoa raw materials that arrive as beans or as processed cocoa ingredients, depending on the plant layout. When beans are used, they are cleaned first with screens and air separation, so stones and husk fragments are removed. The beans are then roasted in a programmed heat curve that drives off moisture and develops cocoa aroma while keeping scorch risk low. Roasting also makes the shells brittle, so separation is efficient later. After roasting, the beans are cracked and winnowed. Cracking breaks beans into nibs without pulverizing shells into fines. Winnowing uses airflow to lift lighter shell away from heavier nib. The nib stream is screened to remove oversized fragments that would strain grinders and to remove dust that would darken and overheat during milling. Nibs then enter grinding to become cocoa liquor. Grinding is a staged reduction where particle size drops while fat from the nib makes the mass flow. Early mills break nib into paste. Later mills refine the paste into a smoother liquor. Temperature is controlled because friction can raise heat and drive off aromatics. The goal is a stable liquor that is pumpable and consistent in solids and fat. Cocoa butter and cocoa powder streams are also managed. Cocoa butter is melted in jacketed tanks and filtered so no solid flakes remain. Cocoa powder is sieved to remove lumps that would create specks. These cocoa streams become levers for viscosity and flavor. More cocoa butter increases flow and melt. More cocoa solids increase intensity and thickness. Milk ingredients are prepared with the same attention to moisture and particle behavior. Milk powder is stored dry and sieved to break clods. Whey powders or lactose powders are handled similarly when used. These powders carry dairy flavor and also influence sweetness and caramel notes during later heating. Moisture in dairy powders must be low because water in chocolate drives thickening and seizing. Sugar is prepared as a clean, dry crystal feed. It is screened to control crystal size and remove agglomerates. Crystal size influences refining load and final mouthfeel. Fine sugar can reduce refining time but can increase dust and handling issues. Coarser sugar can slow refining and increase wear. The line selects a sugar specification that supports consistent refining performance. The first assembly stage is mixing, which creates a uniform pre-blend before refining. Cocoa liquor and melted cocoa butter enter a mixer and create a fat, continuous base. Sugar and milk powders are added gradually so they are wetted rather than floating as dry islands. Mixing uses a strong folding action to distribute powders through fat. The goal is a crumbly paste or thick dough depending on the recipe and the amount of fat present at this stage. In some milk chocolate processes, a crumb step is used to build characteristic dairy notes and to stabilize the milk solids. Crumb production combines milk and sugar with cocoa liquor or cocoa components and then heats the mixture to drive off water and develop flavor. The mixture is cooked until it becomes a dry or semi-dry crumb material. The crumb is then milled and later remelted into chocolate mass. This approach changes flavor and texture because it sets milk sugars in a different thermal history. Whether crumb is used or not, the downstream steps still require refining and conching. Refining is the step that turns the mixed paste into a smooth eating texture. Refining reduces the size of sugar and cocoa and milk particles so the tongue cannot detect grit. This is often done with 5-roll refiners or with alternative milling systems. In DUR, roll refining the paste passes between rollers with decreasing gaps. Each pass squeezes and shears particles smaller. The output becomes thin flakes because the mass leaves the final roll as a film that breaks off. Refined flakes have low free fat at their surface and are prone to holding moisture and air. They must be processed immediately into conching. Conching is a combination of mixing, shear, and controlled heat that changes both flavor release and rheology. In conching, the flakes are worked in a conche where paddles or rotors knead the mass. Heat keeps fat fluid and encourages volatile removal. Shear coats particles fully with fat, which reduces friction and lowers viscosity at a given fat level. Conching is often described as 2 overlapping goals. One goal is flavor smoothing by driving off unwanted volatiles and distributing aroma compounds. The second goal is flow control by reducing moisture and breaking down agglomerates so the chocolate becomes a stable suspension. Moisture control is critical because even small water content can cause thickening. Conchis, therefore, manage airflow and temperature so water leaves gradually without overheating. During conching, emulsifiers can be added to fine-tune flow. Lecithin is a common flow modifier and it reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further at the same fat level. These additions are dosed late because early addition can mask conching effects and can change shear behavior. Dosing is precise because small changes alter how chocolate runs through pumps and through molding heads. After conching, the chocolate is held in storage tanks with gentle agitation. Tanks keep temperature stable, so the chocolate remains fluid. Agitation prevents separation and keeps the suspension uniform. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is smooth and flavored, but it is not yet in the right crystal state for molding. Tempering is the controlled crystallization of cocoa butter that creates a stable set and a clean snap. Chocolate contains cocoa butter that can crystallize in several forms. Only specific forms give the desired gloss and contraction. Tempering builds a population of stable seed crystals and then holds the chocolate at a working temperature where these seeds guide solidification. Tempering is done in continuous tempering machines that heat and cool the chocolate in stages. The chocolate is first heated to melt existing crystals fully. It is then cooled while being agitated so crystals begin to form. It is then gently reheated to melt unstable forms while keeping stable seeds. The output is a chocolate that flows well, but contains the right crystal seeds. Process control uses temperature sensors and viscosity signals to maintain stability. Once tempered, the chocolate is ready for shaping. For bars, the main shaping method is molding. Polycarbonate molds move under deposit heads that meter chocolate into each cavity. The depositor fills to a precise mass because bar weight must be consistent. Molds then pass onto a vibrating table. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate flow into sharp corners and improves surface gloss. After vibration, molds enter a cooling tunnel. Cooling is staged so the surface sets without shock. As chocolate cools, it contracts slightly. This contraction helps release from the mold. Cooling zones remove heat gradually so internal stress remains low. If cooling is too fast, the bar can warp or show bloom later. If cooling is too slow, throughput drops and molds remain occupied. When bars have solidified, they are demolded. Molds are flexed or tapped so bars release cleanly. The bars then move to inspection conveyors. Vision systems can detect surface defects and missing corners. Weight checks can confirm deposit accuracy. Defective bars are diverted for rework. Rework. Chocolate is collected and remelted, then reintroduced upstream in controlled ratios, so crystal history does not destabilize tempering. If the product includes inclusions like nuts or crisp pieces, the process adds an inclusion stage. Inclusions are prepared by roasting or drying and then screening to a tight size band. They are added either into the chocolate before molding or sprinkled into molds before depositing. Inclusion dosing must be consistent because it affects bar thickness and cooling time. Inclusion surfaces must be dry because moisture causes thickening and can create voids. If the product includes layered fillings, the line uses sequential depositing. A chocolate shell may be deposited first and partially set. A filling is deposited next. Another chocolate layer seals the top. This creates a composite bar that requires additional cooling time and more careful temper control. Even then, the same fundamentals apply. Each phase must flow at the right viscosity and set in the right order. Once bars are fully set, they move to wrapping. Wrapping is a mechanical process that protects chocolate from oxygen and moisture and from handling marks. Bars are fed into a flow wrapper or into a fold wrap system depending on the pack style. The wrapper forms film around the bar and makes seals. Seal temperature and dwell are controlled so the film closes without wrinkles. Film tension is controlled so it does not crush the bar edges. Toffifee is manufactured by assembling a layered piece in a fixed cavity sequence, where a caramel cup is formed first, a hazelnut is seeded into that cup, a hazelnut cocoa cream is deposited around the nut, and a final chocolate cap is applied before cooling and tray packing. Production starts with preparing the two high-volume mass streams that define the piece. One stream is a caramel that must be firm enough to hold a cup shape, yet soft enough to bite cleanly. The other stream is a nut cream that must be smooth and pumpable, yet stable enough to keep its shape around the nut. A third stream is tempered chocolate for the cap and for any sealing functions. Caramel manufacturing begins with sugar and glucose syrup handling. Sugar is screened so crystal size is consistent and clumps are removed. Glucose syrup is held in jacketed tanks so viscosity stays stable for accurate pumping. Dairy components are prepared as a controlled liquid or powder stream depending on the recipe design. Fat is melted and filtered so it can be kneaded smoothly into the cook. Cooking is done in a continuous cooker or a batch kettle that is designed for high solids confectionery. The syrup phase is heated to dissolve sugar and drive off water. Solids level is the key target because it controls final chew and flow at the depositor. If solids are too low, the caramel will slump in the mold and stick in tooling. If solids are too high, the caramel becomes glassy and cracks when formed into thin walls. Temperature and residence time are tuned so browning develops to the desired level without scorching. As the cook reaches endpoint, the caramel is cooled to a working temperature where it remains plastic. Cooling is staged so viscosity is stable across the run. The caramel is held in a jacketed tank with gentle agitation to prevent skin formation. This tank feeds the forming depositor through heated pipes that avoid cold plugs. Flow meters and pressure sensors keep the depositor feed steady. Hazelnut handling runs in parallel. Nuts are cleaned and graded so the size band matches the cavity. Roasting drives moisture down and develops aroma while keeping the nut crisp. Cooling follows immediately, so residual heat does not soften caramel or melt cream fats later. Skin removal reduces bitter flecks and improves adhesion in the cream stage. Whole nuts are then singulated so they can be placed one by one. The hazelnut cocoa cream is prepared as a fat, continuous paste. Roasted hazelnuts are milled into a smooth nut paste with controlled temperature so oil does not separate. Sugar and cocoa solids and dairy solids are blended into this paste. Refining reduces particle size so the cream feels smooth rather than gritty. The cream is then mixed under controlled heat so viscosity becomes consistent and air is minimized. Emulsifiers can be introduced to tune flow and prevent oil bleed. The finished cream is held warm enough to pump but cool enough to keep flavor stable. Chocolate for the cap is produced and tempered to a stable crystal form. Chocolate is melted and filtered so no unmelted fragments remain. It is then tempered in a continuous tempering unit that heats and cools in stages. The goal is a chocolate that flows well but sets fast with gloss and clean release. Viscosity is monitored because cap thickness depends on flow through small nozzles. Assembly begins on a tray or belt line that carries a field of cavities. The cavities act as the master geometry for the product. Each cavity receives each component in sequence with tight timing. The first operation deposits caramel into each cavity as a measured shot. The shot is designed to form a cup rather than a flat puddle. This is done by using nozzle geometry and deposit motion that pushes caramel up the cavity walls. Immediately after deposit, a forming tool can shape the caramel cup. A punch or dome tool presses into the caramel to create a bowl profile. Tool temperature is controlled so caramel does not smear or stick. Dwell time is short, so the line speed remains high. The tool retracts and leaves a consistent hollow with a defined rim thickness. Caramel cup geometry is a major control point. Wall thickness must be thick enough to hold during nut insertion. Wall thickness must not be so thick that the bite becomes overly chewy. Rim geometry must be clean because the rim later interfaces with cream and the chocolate cap. If the rim is uneven, the cap can sit crooked and leave gaps. After cup forming, the cavities pass through a short cooling section. This cools the caramel surface to increase strength for nut insertion. Cooling is tuned to firm only the surface layer while keeping the bulk plastic. A fully hardened caramel would crack when a nut is pressed in. A too soft caramel would allow the nut to sink and deform the cup. Nut insertion follows. Nuts are fed from a singulator that orients each nut. A placement head drops or presses one nut into each caramel cup. Placement force is controlled so the nut seats at a consistent depth. The nut must be centered so the final piece balances. Off-center nuts can create thin caramel walls that tear. The nut is pressed enough to anchor without breaking the nut. Next, the nut cream is deposited around the nut. The depositor nozzle enters the cavity and dispenses a controlled volume. The cream must flow around the nut and fill the annular space. It must also avoid trapping air under the nut or along the cup wall. To control air, the deposit can be staged as a first ring and then a top fill. The nozzle motion can trace a small circle to wet the wall evenly. Cream viscosity is tuned for this step. If the cream is too thin, it floods and can overflow the rim. If it is too thick, it bridges and leaves voids. Void formation is a defect because it weakens structure and creates visual gaps under the cap. The line controls cream temperature tightly because temperature is the fastest way to shift viscosity without changing formulation. After cream deposit, the surface is leveled. A small leveling blade or vibration can flatten the cream surface. Leveling ensures the chocolate cap will sit evenly. It also ensures the cap seals the cavity edge without a high spot that would break later. Leveling is gentle because excessive vibration can move the nut and distort the cream ring. Chocolate capping follows immediately after leveling. Tempered chocolate is deposited as a disc onto the cavity opening. The disc must bond to the cream and rim and then set without cracking. Deposit weight defines cap thickness, which controls snap and protects the interior. If the cap is too thin, it can fracture during tray packing. If too thick, it can dominate the bite and slow setting. To achieve a clean cap, the chocolate is deposited at a temperature where it spreads slightly, then stops. The mold geometry helps define the cap edge. Some lines use a light vibration after capping to remove bubbles and ensure contact. Vibration must be limited because it can cause chocolate to run down the cavity walls and change appearance.